Okay. Sorry about that. Okay, well, I guess you all know that the grade is posted. Yeah. So we go to this link here for exam one scores. They're all in order according to that student code, which you can calculate using your G number here. I didn't check to see if there are any duplicate numbers. It does occur occasionally that there's actually duplicate code numbers, in which case you need to email me and then I'll help you straighten out which grade is actually yours. The average was about 73%, which is about what was expected for this exam, so everything seems to be going pretty much okay. Now, okay, so we're going to carry on working our way through atomic structure before we finish chapter 3. But I'm going to review a few things about the spectroscopy before we finish up our discussion of atomic structure. So again, spectroscopy is basically the study of the way that atoms emit and absorb light. We have to use a spectrograph or spectroscope, it's actually a spectroscope, because we're viewing this thing with our eyes rather than recording it with a detector or a camera. So again, a spectroscope, we send light in, it could be white light or anything. In this case, it's white light, passes through a slit, illuminates the prism, and the prism actually spreads the light out because different wavelengths of light have different index of refraction, and they bend by different amounts of angle. So that actually causes the spectrum to disperse out and give us this spread out pattern on the screen. So what we find is that the shorter wavelengths, like blue, actually refract by larger angles than the red. And so that's the fundamental reason that we actually see a spectrum at all when we shine light through a prism. All right, so we shine white light through a prism, and we get a continuum spectrum because it's breaking down the white light into its components. Now again, if this were sunlight, we actually would see some dark lines on that. But if it's pure white light from an incandescent light bulb, for instance, then we actually get a completely continuous spectrum with no additional features at all. Another couple of figures from the book. Again, incandescent light bulb shining through spectroscope gives us a continuous spectrum. Now we've already talked about all the different things that are going on here, so again, by way of review. But there's two ways that we can create emission lines. Okay, two separate ways that we can create emission lines. Method one is we can heat a gas. Shine the light of the heated gas through the spectroscope, and what you get is a set of bright lines on a dark background, which are emission lines. Okay. So again, the contrast is if we use a hot bulb, we actually get a complete continuous spectrum. With emission at all wavelengths, that's a continuous spectrum. But when we shine on heated gas emission, we only get selected wavelengths. And the wavelengths that we actually get depend on the composition of the sample, and actually can be used to identify the sample that we're looking at. So it's kind of like a fingerprint of the element that we're looking at that's doing the emitting. So if we see a pattern on our spectroscope screen that looks like this, we know it's hydrogen. We could see a mixture of two different things, like hydrogen and sodium. We might see a red line and then this bright doublet of the yellow. That would indicate that it's some kind of a mixture. So again, it's the kind of idea of a fingerprint of the substance that we're looking at. Now, absorption lines are pretty much only created one way when we pass light through a cold gas. We find that certain wavelengths are absorbed. So those wavelengths don't make it to the screen, and we have a dart of photon, not Darth Vader, but a dart. There's dirt. You have less or something? English majors? Dirt, not dark. It's Darth Vader, right? You don't have enough of the Jedi warrior, then you get these black lines. Right? It's a lack of emission of those lines. Now what we're going to see is what's actually going on here. We kind of already alluded to this. Sorry. What's actually going on here is that certain wavelengths from this white light. Now white light is a composition of many different wavelengths, right? So certain wavelengths are causing excitation of the atoms in this gas. Now what happens is that we get atomic excitation of the gas, and so we have these excited atoms running around in there, and then they de-excite, and they re-emit a photon that's identical to the photon that caused the excitation in the first place, with one important exception, which is the direction. The photons are originally moving through the slit from sort of from left to right here, okay? But if we allow excitation to take place, then when the de-excitation occurs, the photon that's created doesn't go necessarily in the original direction. It's a completely random process. So what happens is we end up with very few of the de-excitation photons going through the slit and contributing to the spectrum, and that's why we have this dearth of photons at those particular wavelengths. Very important to remember that the absorption and emission lines occur at the same wavelengths or frequencies, say either way, for a given sample. So if you have, for example, hot sodium, you're going to get this doublet here in the yellow when you pass the spectrum through a prism. If you take that sodium and you let it cool down, and then you illuminate it with white light from the back, you get this absorption line, but they're at exactly the same wavelength. So the same fundamental physics of atomic excitation is going on here. We just have a slightly different experimental scenario, and that's why we get emission or absorption. So again, I'll sort of work my way through this and try to continue to clarify this as much as I can. This is a panel I did already show you once before. This has everything in it that we're interested in here, except one process. The one process that's not in this panel is the one that has to do with the hot gas, because there's no hot gas. Right? So remember that this is sort of everything minus one possible process, which is the one involving hot gas. Okay, so if we have a hot bulb and we view it directly with the spectroscope, we get a continuous spectrum. End of story, continuous spectrum. That's actually really black body emission, characteristic of the temperature of that hot filament. So what we're seeing here is a continuous spectrum, but if we plotted the brightness in those different colors, if we plotted it as a function of wavelength, we would get that nice bump, a black body type curve with a peak that corresponds to the temperature of the filament. So the black body looks like a rainbow if we just look at it visually. If we send the light from the hot bulb through the cool gas, again we get the absorption spectrum. If we look at it from an angle though, we have an emission spectrum. So here's that second way of getting emission lines. There's two ways. One is you view a hot gas, which is not on the map, right? But if you heat up a gas and you just do that directly with the spectroscope, you see the emission lines. But this is the second way. We can view a cool gas from an angle relative to its white light source. And that off-angle view will actually also give us emission lines. So there's two ways to get emission lines. Okay, so again, this is sort of everything except the part about the hot gas. All right, so again, continuous spectrum. This is basically, you should have in your mind that this is basically the same thing as black body. We just call it a continuous spectrum because we're just viewing it, you know, as a projection onto the screen or something, rather than plotting it as a function of brightness on it. Emission and absorption occurring at the same wavelength. All right, so again, I'm going to go through this a little more quick. I mean, we've already been through a lot of this. The emission and absorption occur at the same wavelengths and frequencies, and this all has to do with atomic structure. Again, pretty much just high school stuff. We have electrons, protons, neutrons. The nucleus has protons and neutrons. The number of protons determines the identity of the element. The number of protons does that. So we look at this and we see two protons, and we know it's blank. Fill in the blank. Helium. Right. There's just a story on NPR yesterday about the National Helium Reserve, located somewhere in the United States of America. And the interesting thing about the helium reserve is the one thing Congress could agree to fund in the midst of all the craziness that's going on. The one thing they did, they passed the bill. They keep the helium flowing, which is good because otherwise no balloons or happy meals would be done, right? And that then the blank really hits the fan. When you lose those balloons, and the kids notice it's not abstract, right? You don't have your balloon or your happy meals. All right, so this is helium, and this is actually we would view this actually as an ion because there happens to be only one electron orbiting this nucleus. So, in literal terms, if we look at this thing, it has a net positive charge because there's two protons and only one electron. So this entity there actually has one net positive unbalanced charge. So we would actually do this as a form of ionized helium. But it's healing nonetheless because of the two protons. Okay, so again, different states of excitation. This is, of course, simply hydrogen. One proton, one electron. This is neutral hydrogen in two different excited states. We look at this and it looks sort of like an orbit. Okay, we've been through this. It's not really an orbit. It's an orbital, or electron cloud. And what's going on here, again, is pretty mysterious and wasn't really understood until around 1910 or so. Over 100 years ago. How about that? This was first understood as being really a probabilistic situation where we don't know exactly where the electron is. It is orbiting, but we don't know where it is. And there's actually no way to know unless we do a specific observation. And then we will see where the electron is. But it's not like a planet in orbit around the sun like Mercury, or we know exactly where Mercury is all the time. We don't know where the electron is. So this is actually a probability distribution where the density of these blue dots indicates how likely it is that you will find the electron in that specific area if you take a snapshot of this thing. You take a snapshot with a regular camera, well, scenic one, a regular camera, it's magnify enough, but if we use the proper type of equipment, we can actually take a snapshot of this, and the electron will turn out to be somewhere. Now, when we look at the excited state, the electron is generally farther away from the nucleus. So we have this general increase of distance as we go to higher excitation states. But still, we don't know exactly where the electron is. And even in the first excited state, there's a little chance that the electron is rather close to the nucleus. So we don't know the exact distance. But the thing that we do know is the exact energy. The energy is exactly known precisely. Okay? And that, of course, is the key fact that relates the structure of atoms to the specific wavelengths that we see in emission and absorption. All right, each orbital has a precise energy, meaning, that's another way of saying each excitation state of the atom has a precise amount of energy that's stored in that atom. All right, so here we have our standard contestant in the audience, which is hydrogen. The reason hydrogen is the most likely studio contestant is simply because hydrogen is over 85% of the universe. So in an average audience, you're going to have mostly hydrogen atoms volunteering to participate here. So here we have a hydrogen atom that's in the ground state. And along comes the wrong kind of radiation. You see the yellow not possessing the energy that corresponds to the jump from the ground state to the first excited state. We have to supply energy in exactly the right dose, or it simply gets ignored. It's the cold shoulder phenomenon. The yellow light just passes right through there. Likewise, green, ignored. Red happens to have the right wavelength, therefore the right energy, has exactly the energy that's required to create that jump, that difference. Okay, so now we have an excited hydrogen atom over here. And what that can do is spontaneously de-excite by emitting a photon. So what you've seen, if we go from the original before state of a ground state hydrogen to this after state over here, which is again a ground state hydrogen, the actual difference that took place was we had a red photon coming in from the left. Remember, it was coming in from the left, but it emitted off in some other random direction. So if you want to think of it in net terms, what's really happened here is that the photon was absorbed and then re-emitted in another random direction. So it really just kind of randomizes the direction of the original photon. And of course, it ignores all the other photons, except the ones that have exactly the energy that's necessary. So if we want to think in terms of a spectroscope, okay, if we think of these atoms as being part of a cold hydrogen gas, right? We have this cold hydrogen gas and we back illuminated it with white light, right? So here we have, let's pretend this is actually in the excited state, but let's pretend it's in the ground state. And we've got white light over here. We're shining the white light. Most of the photons go right through and end up on that screen that we saw, because there was mostly a continuous spectrum on the screen. Remember, there were just absorption lines, but it was mostly a continuous spectrum. The reason it was mostly continuous is because most of the components of the white light are simply ignored and they just pass through. Unaffected, and they